hence it is a vector. Force is measured in newtons, capital N, where force is equal to mass in kilograms times acceleration due to gravity. And on Earth, acceleration because of gravity is 9.8 meters per second squared. So when we're looking for force, it's always 9.8 times your mass. So for example, determine the force acting on an object with a mass of 1 kilogram. So to find that force, we just have to multiply 9.8 times 1 kilogram. And so it's 9.8 newtons. Here we have 50 kilograms, so we just do 9.8 times 50, which is 490 newtons.
Miss?
Yeah.
Do we also have to include a direction, or does the plus and minus, like, I mean, the sign of the answer already signify a direction?
What do you mean? I don't know what you mean. Right now, when I'm trying to find force right now, or just as we go ahead?
Well, for these examples, I mean, because it should have a direction as well, right? Unless the sign already includes the direction.
But mass is a scalar, right?
I'm sorry?
Mass is a scalar, right?
Mass is a scalar, yes. However, force is, your force is not. Your force is a vector.
I mean, like, do you have to put a bracket and put down, like a square bracket and put down, or is this already enough?
I'm going to say that for this type of a question, this is okay. And
Okay.
the reason is, I'm going to tell you why. So we're basically dealing with gravitational force, which is always in what direction? Down. Right? Your gravitational force is always pulling down. So it's okay. I would accept just this. Cool?
Okay, thank you.
You're welcome. To be honest, well, you could be asked a question to find force. You could. But yeah, I would accept it. You don't need to put down. I mean, you could. You're not going to lose marks if you do, but you don't have to here. Okay, resolution. Taking a single force and decomposing it into two components. So you guys we've already talked about component form, and you're already understanding that the components are what are the slope of that vector, right? They make up the slope of what that vector is, the rise and the run. And so when we're resolving vectors, what we're doing is we're looking at the two forces that are perpendicular that form a right angle triangle. Okay, so you're looking at the components. So we call this the force on X, and here is our force on Y just because of the axes. So there are three basic types of questions involving force. The first one we're going to look at is resultant. So these types of questions are when you're going to be finding the resultant, just like we've been doing so far. Okay, so obtained by adding the separate forces acting on an object. So for example, a load is being pulled by two ropes, one rope at 15 degrees with the horizontal with a force, one rope at 15 degrees with the horizontal with a force of 8 newtons, and the other rope on the opposite side of the horizontal at 20 degrees with a force of 10 newtons. Determine the resultant force. So here, I have to label my two ropes. So this is almost like an aerial. My position diagram here, here's the load. And I know that we have a magnitude of 8 newtons here. And here we have 10 newtons. And one rope is at 15 degrees with the horizontal. And the other is 20 degrees. So two ropes that are pulling this load, okay? And it's almost like an aerial view. Well, now we want to come up with our force diagram. So because we're looking for the resultant here, we know that we're always arranging from tail to tip. Okay, so here's my first vector, and that's my 8 newtons. And now what I want to do is I want to take my second vector and displace it here. Okay, so that's my 10 newtons. And this is my resultant. Does everyone see that? Okay, so placing the vectors from tip to tail, and there's my resultant. Well, I need to solve. So I need to solve for R. Do I have enough information to solve for R? Not the way it's labeled right now, but what can I do? How can I solve for R? What information can I gather from this first diagram, and where do I put it in my second diagram?
Do Z pattern to find that the angle at the top to the left is 15.
Yeah, you could. We could totally do a Z pattern. And you know that that's 15 degrees. Absolutely. Z pattern. We could also do a C pattern here. And you can do a C pattern because we know, so this is my 20. So we know that this angle here, 15 plus 20, added with this angle here has to be 180. So I can find that angle there by using a C pattern. And what would that angle be?
$145.
Good. Now I think I'm ready. What do you guys think? Do we have enough information now?
Yeah. Yep.
We're good? Okay, so what am I going to use? How am I going to solve for R?
Cosine law.
Yeah, cosine law. We have two sides in the contained angle, so we know it's cosine law. Bless you. And what do we get?
17.18.
Good. I'm just going to round it to 1. Good. So 17.2. Am I done?
Wait, if we were to use the Z pattern, how would we write it?
What does that mean if you were to use the Z pattern?
Like
Right
to
here.
find
Look,
the
I
15
like-
degrees.
Look. Do you see that? I showed it right here.
No, I mean like how would we like show that we used it?
Oh, it's just, you can just do this. Oh, sorry. Just write Z pattern on your diagram.
Okay, so there's nothing we
Like,
need.
see how I highlighted it? And then you could just do. Done.
Okay.
Cool?
Yep.
Okay, am I done? We
Need to
want
find
the
the direction.
resultant force. Yeah, no, we're not done. It's a vector. And so we need the angle. So what angle am I looking for here? What angle am I looking for?
In between the red dotted line on
Good.
the
What do we
left,
call that? What do we call that?
the normal.
The horizontal.
Okay. And the green, yeah.
Yeah, perfect. Okay, so we want between the resultant and the horizontal. That's what we're looking for here. Okay, between the resultant and the horizontal. So you can make a note of that. We want the angle between the resultant And the horizontal, I've called it alpha. And so now to solve for it, what am I going to do? Okay, guys, so what am I going to use to solve this?
You can use sine
Solve the whole angle.
to find the whole angle and so then subtract 15.
Okay, so sorry, did I hear a sine law? So good, you're going to find the sine of the whole angle. Very good. Sine of theta over 10 equals sine of 145 over 17.2. So go ahead and find theta. Once we find theta, then we're just going to subtract to find our alpha. Cool? So go ahead and do that, and I'll be back in just one sec. Okay, guys, I'm back. Sorry about that. All right, so sine law, what'd you guys get? What was your theta?
19. Wait.
Yeah. Almost.
I got like 19.448.
Sure. Okay, so 19.5. Now, that's not the angle we want. We wanted alpha. And so I do 19.5 minus 15. And you see that alpha is 4.5 degrees. And again, that is your angle between the resultant and the horizontal. Please make note of that. And now we need our statement, which is therefore the resultant force is 17.2 newtons at 4.5 degrees below the horizontal. Are there any questions?
Would you be allowed to say 19.5 degrees from the 8 Newton force down or something like that?
So you want to say 19.5 from where?
Degrees. From the 8 Newton rope force.
No, from the horizontal. You're always going to be giving me from the horizontal here, okay, in this case.
Okay, thanks.
Okay, yeah, no problem. Okay. So now you can do this using components as well. And I think what I'm going to do, I think I have it. No, I don't. I should have it. Okay, give me 1 sec. I'm going to get it already done because I don't want to have to do it all again. But you don't have to do it the way that I just showed you. A lot of you guys who have taken physics are used to doing it using components, and that's okay too. So I'm just going to pull up a file that shows how to do it with components. And it's just by using the right angle triangles instead, right? So you're going to be finding your forces separately and then adding them together. So hold on, let me just find it for you. Smart. And we're doing, it should be here. Let's hope. There we go. And so this is how you would do it using components. So for those of you that have not taken physics and are not comfortable with this, then do it the way that I showed you. For those of you who prefer to do it this way, you may do it this way. Okay? You may do it this way. So notice, guys, that we're doing it as 2 separate triangles. Okay, 2 separate triangles, the 2 forces. Okay, and then once you get your 2 forces, you want the resultant, and so you add those 2 together, okay? Notice here, guys, it's the Pythagorean theorem, right, for your resultant, and so that's why it's squared. See how it says, there, it shows it right there. There you go. Okay, so anybody who wants to do it this way, you may. You don't have to, though, if this is your first time learning this, okay? Then just do it the way that I showed you. Let's get back. How do I get back? Smart. There we go. What do you mean? Oh, this. That's just, yeah. Okay, so let's go back. All right. Are there any questions, or is everyone good so far? All right. So now a different type of question. What about if we're talking about something being in equilibrium? So when you're talking about objects that are in equilibrium, it means they're not moving. So it means you're applying some sort of tension. So an example of this is when you're, for example, hanging something from 2 ropes. Okay, that's a good example of something being in equilibrium. And so the object doesn't move. Okay, has the same magnitude but opposite direction of the resultant because you're trying to keep the object from moving. Okay, so you've got the forces now in the other direction. The net force of all vectors acting in a state of equilibrium is 0 because, again, the object is not moving. So take a look here. Normally, when we draw our force vectors, we don't do it like this. Look, we've got one there. There's my next one. Normally, the resultant would be like this. But in this case, because we're in a state of equilibrium, we have to use what is called the equilibrant. And the equilibrant means that it goes in the opposite direction. So it's this guy. So what you're noticing is that you're starting and ending at the same position. Okay, which is not what we do with resultant vectors. Okay, so please just take note of the difference. Okay. All right, so here we go. Force 1, force 2, there's my resultant in red. Well, what's the equilibrant then? It is the exact same direction, however, excuse me, it is the exact same force, but in the opposite direction. Okay, so they're parallel, but in opposite directions. All right, recall, triangle properties. Is it possible for three forces, forces of 5 newtons, 10 newtons, and 17 newtons to be in a state of equilibrium? So what I want you guys to do here is draw your triangle. And so I have my forces, and this is my first force, which is 5 newtons. And I have my second force, which is 10. And all you have to do is see if this is possible. So is it possible to create this triangle? So what you can do is use the cosine law, because I have 3 sides, right? And you try to solve this. And when you try to solve for theta, you're going to get math error. And so then the answer is no. Another way that you could do this is by realizing that in any triangle, A plus B always has to be greater than or equal to C. And in this case, 10 plus 5 is less than. 10 plus 5 has to be greater than or equal to 17, but it's not. Okay. So in this type of question, you want to see if it's possible to create the triangle. All right, so let's take let's look at an example of this type of question. So we have 2 ropes that are 50 centimeters apart, and they're being used to suspend a weight of 5 kilograms from the ceiling. Okay, so something that weighs 5 kilograms is hanging from a ceiling. And so hence it's not moving, right? It's just hanging there in the middle. So we need tension. So if each rope is 30 centimeters long, determine the tension in each rope. So let's start by labeling. All right, so I know that my weight is 5 kilograms. I want blue. 5 kilograms. What is this force here, guys? This down force, what is it?
Gravity.
Yeah, good, it's gravity. It's our force of gravity, right? Pulling on the weight. Good, excellent. And then I'm gonna have, I'll call this tension 2. This is my vector. And this is tension 1. Okay, these are my 2 vectors, my 2 tension vectors. And both of these vectors make some angle with the ceiling. All right, so now I want to come up with a force diagram. So in order for me to come up with a force diagram, then I need to have my vectors from tip to tail. And so I'm starting with tension 2. That's what my diagram is showing. And then I'm adding tension 1. And normally we would be going in the opposite direction, but because it's in a state of equilibrium here, we know that the arrow is down. Okay, so what can I label here? Help me out. What can I label on this diagram?
We know T1 and T2.
We
Are
do.
30
Oh, our what?
centimeters.
Our what? Say again.
T1 and T2
Mhm.
are 30 centimeters.
The length of the rope is 30 centimeters. But if I'm talking about now tension as a vector, right? Because it's my force. Tension is my force. So I don't know the magnitude of my tension.
Sorry.
Do I?
Yeah, we know the gravity.
Okay, we know gravity. So we can find the gravity very easily. Yes? Very good. So looking for gravity, the magnitude of gravity, what would I do?
We can just multiply 9.8 by 5, right?
Very good. That's all you got to do. And we know that it's 49 newtons. Okay, very good. We know the force of gravity. Excellent. Next, what else can I do? What else can I label in this diagram?
Theta.
Theta, where? Excellent. Where?
In between the horizontal and T2 and also in between, yeah, there.
Perfect. Excellent. So this one we can see. The first one we can see just right from here, right? I'm just copying that right here. Well, now when I take this vector and I move it here, then we can see that I have my angle theta here. Yes, do you guys see that? By the Z pattern? Do you see it? And so there's my angle theta as well. I want to make sure you guys actually see this. If you see that, you can see that you also have theta here, which means that when I displace this vector, I would also have it there. Okay? Or you can see it from a straight Z pattern as well, right here. Right? Even better. Okay, good. So I can label those. That is excellent. What should I do next? What should I do next? Talk to me, guys. We found this. You're right. That was 49 newtons. Yeah, tell me.
We can do cosine law, but we should put like the magnitude of T1 and T2 like under the same variable.
Put as the same. Well, you're right, because you're saying that T1 and T2 are going to be equal. Is that why you're saying that?
Yeah.
Yeah, you're absolutely right. They will be equal. If we didn't want to assume that they were equal, what can I do to help me out here? Is there anything that I can figure out from my first diagram to help me out with my second? Is there anything that I can solve here?
The angles,
Yeah.
cosine law.
Yeah, very good. I can use the cosine law to solve for theta. I can find out what theta is from my first diagram. And so I'm going to use cosine law to solve for theta. And you guys tell me, go ahead and do this and tell me what theta is approximately equal to. Give it to me to 1 decimal place. Anyone? Did anyone get it yet? What's my theta? And I guess I'll show you after. What's my theta here?
$33.6.
Excellent. And then I want 2 theta in my second drawing. And so I can see that that's 67.2 degrees right here. Okay? Good. Now, just so you guys know, in this case, just because we do have two ropes that are equal in length, you could have even used SOHCAHTOA to find that angle, right, of 33.6. I could just drop a perpendicular, and I could have used SOHCAHTOA as well. But both are correct. Do you guys see that? And I would use 25 as my length at the top there. Okay, either way. Okay, I'll just make a note of that here. Good. Okay, so we found our angle. What can I do next? Am I ready to go ahead and solve?
Solve for another
ready?
angle.
Yeah, I need to solve for another angle. Good. So how can I do that?
T1 with the horizontal is theta. And then you do 90 minus that.
Good, excellent. Okay, and I'll call that theta 1. Cool. Okay, what do you think now? Now can I solve? Do I have enough information now to solve for tension 1 or tension 2? I do. I can use the sine law now. I have enough information. I have my angles and one side length, 2 angles and one side. So it doesn't matter if you solve for tension 1 or tension 2. And so using the sine law, I can say the magnitude of tension 1 over the sine of 56.4 is equal to 49 over the sine of 67.2. And then we cross multiply. And we see that tension is approximately equal to tension is approximately equal to
44.27.
sure. So 44.3 newtons. And we have an isosceles triangle. And as we've already mentioned, so we know tension 2 has to be the same. So we say therefore, the tension in each of the ropes is 44.3 newtons. Are there any questions? Okay. Okay. All right. For our last example, we are going to look at forces acting horizontally and vertically on an object, hence forming a right angle triangle. And because we're forming a right angle triangle, we are using components, right? So give me 1 sec, guys, and I'll be back to do this example with you in just 1 moment. Okay, I'm back. Sorry, guys. Okay, I've got my little guy who's in grade 1, and so, I don't know, he's having a little bit of difficulty here and there. Something pops up on his screen, he doesn't know what to do, so getting out the proper books, you know how it goes. All right, so third example. So we've got forces acting horizontally and vertically on an object. So 100-kilometer load is resting on a ramp that is inclined at 12 degrees. Okay, there's your ramp, inclined at 12 degrees. Determine the components of the force of gravity parallel to and perpendicular to the ramp. So this blue vector here is my force of gravity. And I know that because it's pulling down, okay, on the load there that's on the ramp, okay? Then I would need a parallel and a perpendicular force. So here's a force parallel. And I need a force perpendicular, so it's got to meet here at 90. So let's say, wrong way. I don't want my arrow that way. I just want to extend it through. Not the best 90-degree angle, but you get the idea. And so there's my perpendicular force. Okay, so now I want to draw a force diagram. So what do? What do you guys think? This here?
Find gravity.
Yeah, this is gravity. This is not gravity. This is which one? Which force is this?
Perpendicular.
Yeah, that's my perpendicular force. Good. So I'm just going to call it G perp. And then my force of gravity, I'm going to keep vertical. Okay. I'm just going to take this off for a sec. Can I move this guy? Okay. All right. And then my parallel force. We know is this. And of course, it can be displaced here as well. Let's bring that down. All right. So now I want to label this triangle. Who can help me label this triangle? Here's my force of gravity right here. And I know that my force of gravity is what?
998, I think, in this case.
980, no?
Yeah, sorry, 980.
Yeah, it's okay. So this is 980 newtons. Okay. All right. Well, I need more information if I need to solve for my G perp and my G parallel. I need more information. So what can I do? I need some angles here. So looking at the first diagram, let's take a look. I know that this is 90. If that's 90 and that's 12, I can solve for this top angle. And this top angle is 78 degrees. So I'm going to put it here because I think this helps you guys. We know that this is 12. Okay, so from here, now I know that this is 12 degrees. And I know a lot of you guys intuitively can see that that's 12 degrees, but for those who have not taken physics before, I like to show them how we can solve for that 12. So there's your 12 degrees. By the Z pattern, I can see that this is 78. And now I'm ready to go. It's a right angle triangle. And so I'm ready to solve using SOHCAHTOA. So I can use sine, and I can say sine of 78 is equal to the magnitude of G perp over 980. And that's telling me that is equal to, what do you get? When you cross multiply, what do you get here? And then here, I can say the cos of 78 is equal to my other force. I'm missing an L there. Parallel over 980. And go ahead and solve for this one, and I'll be back in just 1 second. And you can round it to 1 decimal place, okay, guys? 1 decimal place, just give me 1 sec. Yes. Okay, I'm back. All right, so what did we get here, guys? What was this force?
G perp is 958.58.
Good. Newton. And parallel, the parallel force was 203.8. So guys, again, very simple math. It's just a matter of learning how to do your force diagrams. Okay? Good.
Wait, Miss, doesn't matter how we draw our force
Nope.
diagrams. It looks a little different than that.
No, you can even
Okay.
do it this way. That's what I have this guy here for. So another way that you could have drawn the force diagram, here's my, we called it G parallel. And then here's my force of gravity. And then I can say that this is my perpendicular. So you can also
Yeah.
do it this way, okay? Whatever you guys are used to. I know that a lot of you guys have already been exposed, and so then you can do it this way, okay? That's acceptable as well. The only thing that I'm gonna say is just make sure your force of gravity is always pointing down. That's all.
And do we need to show work for solving the triangle, or can we just write the angles?
You can just put in the values, it's fine.
Okay. Okay.
Yeah, you can just put in the values. Okay, So here, we're gonna say, we need a statement, of course, and we say, therefore, the gravitational force parallel to the ramp and the gravitational force perpendicular to, sorry guys, I'm using my shorthand here, to the ramp is 958.6 newtons. And I don't know if you guys noticed, but the PDFs that I'm posting are not the ones that I'm doing. These are very messy. So I'm just putting up past PDFs, like ones that I've done in the past, okay? So that's what I'll do for this as well. Cool? Just so that at least you're seeing a neater lesson. Okay, and this is the homework for this section, guys. Page 362, numbers 1 to 3, 5, 6, and 8 to 20. Okay, tomorrow we are going to continue with chapter 7, and then Friday is your test.